Okay, welcome back to MACSMIN after the lunch. My supervisor, Vitaliy Kurlin, is going to give a talk now on geometric data science, establishing 3 principles of atomic geometry. So please take it away.
Thank you, Dan, for your introduction. Yeah, first time experience. Indeed, so I will be presenting the work of our data science group, including many members, and Dan will talk right after me. So geometric data science studying many different objects, but starting from the first very basic and fundamental question, same or different, asked for molecular graphs. So you have seen graphs in Yuri's talk this morning, clouds of unordered points when we have pure atomic centers, even without chemical elements or without covalent bonds, and periodic crystals, which will be discussed in my talk and in several talks after me. So why is it a non-trivial question? Because all these objects can have different representations that might actually refer to the same object, but we should clarify what exactly we mean by the same, because this question, same or different, appears even in titles of crystallographic papers. So for periodic crystals, we consider all types at the atomic level. You might have guessed already the crystal on the left, especially if you have seen some of my early talks, a metal organic framework on the right-hand side. So these pictures illustrate that we work with materials at the atomic level. And we will be asking the question, what is a crystal structure? What crystal structures can be or should be called the same? And if they are not the same, which is usually the case because of noise, how much they differ? So formal mathematical introduction. To define a crystal, or more exactly a periodic set of points, we start from a basis which generates the lattice as the collection of all integer linear combinations of these basis vectors. And then, in addition to a lattice, to get a more general crystal, we fix a finite motif of points or atoms inside a unit cell, which is also generated by this basis. And then the periodic set of points is the following sum: a lattice plus a motif. So more exactly, we consider all possible sums of a vector from a lattice and a point from a motif. So all these sums will generate infinitely many points, a periodic set of points. However, even these simplest pictures illustrate that starting from very different bases, we could generate exactly the same lattice pointwise, or even we could fix a unit cell, we fix a basis here, but start from different motifs inside this fixed unit cell, and then get as a result the same, or more exactly, almost the same periodic set of points, which differ formally here by translation. So let's clarify what we mean by equivalent sets. There are many concepts of an equivalence relation. It's a binary relation that should satisfy the following 3 basic axioms, and transitivity will be especially important because exactly this transitivity axiom justifies a well-defined classification, namely a splitting into disjoint classes. So for crystals, we could consider many different equivalence relations. For example, by composition. Yes, but diamond and graphite consist of pure carbon and have very different properties. We could choose another property, say density, or any property you like. However, you could easily imagine that we could have crystals with very similar densities, but different by other properties. Space groups types. Yes, they have been known since the 19th century, so 230 classes. However, many different chemical compounds, chemically different, they have the same group. That's why it still makes sense to consider finer classifications. So how do we approach this problem? We look at a real crystal. So this is my favorite example, crystal of, like, is it recognizable for Berthold?
Silicon.
Yes, absolutely correct. So you see, it's great to have always an expert in the audience. It's a rough crystal of silicon, so widely used in modern electronics. And when you look at this crystal, it looks rigid. So what does it mean? When we translate or rotate, especially under the same ambient conditions, the crystal structure remains the same, although a representation of this periodic crystal might look very different in different coordinate systems. So that's why we argue that since crystal structures are determined in a rigid form, the strongest equivalence in practice is rigid motion, which is a composition of translations and rotations. So there is really no sense to distinguish crystal representations if they are related exactly by a composition of translations and rotations. We could also add reflections, and in that case, we get a slightly weaker equivalence called isometry in informatics, which doesn't distinguish mirror images. And that's how we have come to the following definition. A crystal structure is a rigid class of crystals, or more exactly, it's a collection of all infinitely many periodic crystals represented in traditional crystallographic information files, but they all should be equivalent within the same class under rigid motion. Or if you would like to slightly modify this definition, slightly weaker under isometry. So that definition looks rather abstract, so mathematically it's well defined, but we have infinitely many representations of the same crystal structure. That's why the next and important practical question is to efficiently recognize this crystal structure and distinguish it from other crystals. And in mathematics, we do it actually every day. And our classical conventional tool for that, for any classification, is called an invariant. So it's a property or function on our objects that should be preserved under our equivalence relation. As a result, it is defined on classes, on equivalence classes. So here I use word isometry as the main equivalence, but only for simplicity because it's a shorter word. So we remember that rigid motion is stronger. So I'd like to map isometry classes of point sets, not necessarily periodic, also finite point sets are an important class for molecules, to some simpler space, for example, numbers, vectors, matrices, where comparisons are easier. So another definition of the invariant, so if any given objects, for example, crystals are isometric, then the invariant should take exactly the same value on these equivalent objects. Equivalently, if an invariant takes different values, then our underlying objects are certainly different, not isometric. Now that's why invariants are useful, because if they take different values on our objects, then they distinguish these objects. Of course, not all invariants distinguish everything. For example, density is a very simple and nice invariant, but it doesn't distinguish all, and chemical compositions are another invariant that doesn't distinguish all crystals. That's why we are looking for stronger, ideally complete invariants that will distinguish everything. So I will explain these words in further slides, but let me motivate the main feature of crystals, that they're discrete in the sense that atoms cannot be very close to each other. However, atomic coordinates take real continuous values, and of course, these atoms vibrate. So even in this crystal right now, it's above absolute zero temperature, atoms inside vibrate. So if we determine this crystal structure, especially under a different temperature, then we'll get slightly different atomic coordinates. That's why it's important to remember that all these atomic positions are not certain, and it's important to quantify these differences. So here, this is an illustration of a simulated crystal compared with a real structure in the Cambridge Structural Database, and our colleagues in material science consider them as the same, although you can easily see differences, slight differences. So when we restrict our attention to 230 space groups in 3 dimensions, it basically means that we split our continuous space of crystal structures into 230 regions or countries. Well, actually, a similar number of countries on our planet, but with boundaries between countries are often rather artificial, And it's important to remember that we live on the same continuous planet, and crystals do exactly the same. They live in a continuous space. So that's why it's important to continuously study them. So in addition to an invariant, one more important ingredient in all our research is a metric, or more exactly, a distance metric. So here, a distance metric is a property or a characteristic of two objects. So it's a distance for a pair of objects, not a characteristic of a single object. This distance should satisfy three basic axioms. And for example, for a complete invariant, the first axiom basically means that we can distinguish our crystals, because if the distance is 0, this happens only for isometric objects. However, an invariant itself, a complete invariant, is insufficient because we can easily define a discontinuous metric on complete invariants. 0 for equivalent objects, say 1 or any other constant, positive constant on non-equivalent objects, but this binary classification is rather impractical because under a small perturbation, our object will change. And also, let me highlight the importance of the triangle inequality. Hopefully, you might remember it from school, but it is required not only for Euclidean distance, but for any other metric, because if you allow this triangle inequality to fail, even with any small additive error, not satisfying this inequality, then the results of popular clustering algorithms, K-means and dbScan, can be simply predetermined. So you could design, you could first choose your clusters and then design a distance which is not a metric, so failing the triangle inequality, that gives outputs predetermined clusters. Okay, this slide summarizes the challenges that crystallography has faced over many years. So in the background, in the first row, you see the hexagonal lattice. And it's infinite and periodic, but it's very tempting to start comparing periodic objects such as crystals by taking finite portions. Well, they could be big enough. So here I have some small examples, but you can imagine even if I increase the size of these boxes or balls, the conclusion will be the same. You could easily find many boxes or balls of the same size, but with different content inside, even with different numbers of points. That's why we should not forget about periodicity. We should not restrict our attention to a single, even a big subset of a periodic structure. If you remember about periodicity, there is ambiguity with choosing a basis and also rotations. So our hexagonal lattice might look very different if we specify the basis. But most importantly, what happens under perturbations, the hexagonal lattice, a primitive, so minimal by volume cell is small, so with parallelogram. And this yellow cell is not primitive, so-called centered rectangular or conventional cell. Yeah, nice rectangle, non-primitive, it can be made smaller, but under very small perturbation, if you shift every central point here, so this one and all periodic copies in other rectangles, just a little bit, then this non-primitive cell initially becomes primitive. So we get a different periodic crystal structure with a twice larger cell, or we could make it 4 times larger or any times larger. So we could scale up it arbitrarily. As a result, so this example, of course, extends to any periodic crystal. You take your favorite one, double a unit cell, and shift only one atom to make the primitive cell large. So it means that any periodic crystal can be considered within the subspace of crystals with the same number of points, 1 or 2 or fixed number, but also the same crystal, any crystal is infinitely close to a much larger subspace with doubled number of atoms in a unit cell or tripled number of atoms. So there are infinitely many layers in this continuous space. So from a mathematical point of view, this is a very single space. So totally singular. Every point is a singularity. Any questions so far?
Just a comment, that's modulation, basically. What they describe is called modulation.
Modulation.
It can even be incommensurate, so the become.
Yeah, you are right. So far, see, we considered only pure periodic crystals. And even in the space of pure periodic crystals, we have...
Yeah, sure. You can get as large as you want.
Yeah, exactly. So now we state the problem. And previously, we considered several partial cases for isometry, motion point sets. Actually, that problem, so the conditions of this problem, they make sense in much more general situations. You could start from any object and any equivalence relation. For simplicity, we consider discrete sets of unordered points, which could be finite or periodic. But in general, this could be graphs or even surfaces or other more complicated objects. So what we require are the following conditions. Invariants we have discussed. In the language of computer science, it means that this descriptor I should have no false negatives. Completeness means that we should have no false positives. Continuity here is stated in the Lipschitz sense. So it says that if we perturb every point of our initial set S up to epsilon, so within its epsilon neighborhood, then the invariant should change. But it should change only a little bit up to a constant. So with Lipschitz constant lambda times our maximum amount of perturbation epsilon. Do you think this is a difficult problem? Do you remember if I have stated all conditions or not yet all? Not yet all, because, well, we could consider easily invariants of some infinite size, say, taking all isometric images of our object. So it's abstractly correct, but not practical. So more practical conditions are, we would like to be able to reconstruct our object from an invariant value. Well, reconstruction, of course, uniquely only under, say, rigid motion. But here add the words in a continuous way to highlight that after we get such a complete and continuous and invertible invariant, we would like to guarantee its inverse continuity as well. So it was actually stated explicitly for protein backbones, so that case was solved. Computability. So here we say polynomial time. So time here means algorithmic complexity with respect to the input size. And what's our input? If it is a finite set, it's the number of points. If it is an infinite set, then it's the motif size, so how many points or atoms we have in a unit cell. So all these objects are invariant, metric, and the reconstruction, they should be computable in polynomial time. So this is a serious restriction. The final condition, so it looks here a bit informal. We would like to have an invariant not only complete, continuous, computable, reconstructable, but also simple enough. What does mean simple? It means that we like to have a description of all realizable values of this invariant, so that we could take a new value and realize this new invariant value as a real object. So this sounds a little bit abstract. That's why I usually give one simple example where when this problem was solved. In the finite case, starting, if you start from 2 points, it would be too easy, but already for 3 points, the problem is interesting and non-trivial. So for 3 points, I hope everyone remembers side-side-side theorem from school geometry. And indeed, well, in school geometry, we study triangles or clouds of 3 points, and well, congruence, or we call it isometry in mathematics. And two triangles are congruent if and only if they have the same triple of sides ABC. If our points are not ordered, then we are allowed to permute with interpoint distances and put them in increasing order. And in addition to increasing order, there is only one extra condition that makes all these triples realizable by real triangles. We need to have the largest distance C not greater than the sum of two smaller distances. And that's it. So you can even visualize that space. So these three inequalities, they define a triangular cone here in the coordinates ABC. For example, the diagonal in this three-dimensional space, when A equals B equals C, so it represents all equilateral triangles. There are also two planes that represent isosceles triangles, and that flat boundary here, we have degenerate triangles with 3 points in a straight line. So if for simplicity we take additionally composition of isometry with uniform scaling, then this three-dimensional cone becomes even simpler than a yellow two-dimensional triangle. And our geographic style space of triangles now is really simple. You simply choose any point in this yellow triangle and you get a unique three-point cloud, unique under isometry and uniform scale. So that's it. For 3 points, the problem has been solved, and it would be nice to have something simple like that for more complicated cases. So how about 4 points? I learned about this example only about 2.5 years ago. So I studied geometry for a long time, I would say for dozens of years, but only 2.5 years ago, I found that there are infinitely many pairs of the following clouds of 4 points in the plane. So in the plane, we have 3 common points, P1, P2, P3. These green points are common. And then in one cloud, we have P4 plus that point. And in another cloud, instead of the orange point, we take the blue point. So hopefully the picture on the right demonstrates that these two clouds, well, clearly not isometric, so not related by isometry, but they have the same 6 pairwise distances. And actually, these points, you see, depend on 4 free parameters. So A, B, C, D here could be any real positive numbers, and you get always such counterexamples. So the naive extension of the SSS theorem even to 4 points in the plane doesn't work, and it obviously opens the question, what invariant can distinguish these clouds? So now, let me go back to the periodic case. So in our research, historically, we started from periodic crystals, but then realized that our invariants work in the finite case. So we made advances in the finite case and then go back to the periodic case. But let me introduce the first invariant. Well, historically, it wasn't the first, but it's the simplest. The simplest is repeated here for the square lattice, hexagonal lattice, and the honeycomb structure when we have more than 1 point in a unit cell. So if it is a lattice, we have 1 point in a cell, and it could be fixed at origin. So let's fix it, and then look at distances to neighbors. So we write down not vectors, not indices of neighbors, but only distances. So pure distance values. And the unit square lattice, the first 4 distances are equal to 1. Then we have 4 neighbors at distance root 2, 4 neighbors at distance 2, and so on. So they are increasing. For hexagonal lattice, these distances are increasing in a different way. And if it is a more complicated periodic point set, then one simple way to get an invariant from this construction is to take the average over all motive points, so that we don't have any dependence on order. Okay, so you might think when we order, when we take the average, we lose some information. Yes, in theory, but although in practice, you will see this is a really strong invariant because formally it's an infinite sequence. An infinite sequence, and it contains already a lot of information. But not to lose any information on the averaging, we can do the following construction. Called it pointwise distance distribution, and later realized that the same, or well, similar exactly, actually, the same invariant was considered by many other people in the finite case only, not in the periodic one, in the finite case, simple case, under different names, for example, local distribution of distances. But we are sticking to the name PDD because it came here from the periodic case. So in the finite case, again, this is a pair from the same family of clouds of non-isometric sets with the same 6 pairwise distances. Actually, well known in crystallography, it's a classical example. So to distinguish them in a better way, not by taking all distances together, we can initially fix one point, say top left vertex, and then look at neighbors, or more exactly, again, distances to neighbors. So we write down distances to neighbors in increasing order. Root 2 to root 10, so for the top left vertex. And then for the top right vertex, similarly, due to symmetry here, we get exactly the same distances to neighbors. So of course, where different neighbors, we don't look at indices or anything. But since we have the same rows, it's convenient to merge them, collapse them into one row. And to remember this collapse, we assign the weight. So here, 2 of 4 points have the same distances to neighbors. So the weight is 1/2, 50%. And similarly, the bottom vertices in this trapezium, they have a different but equal another row of 3 distances. For the kite example, the PDD is different. As you see, the invariant obviously became stronger. And I should mention, since we discussed homometry yesterday, or pair distribution function, so experimentally available for crystal structures. So PDF looks very similar to PDD, but it's a weak invariant because all distances are combined into a single distribution, while we split them per point. So these two sequences, so you see it's a one-dimensional example. 2 sequences depending actually on one free parameter R. They are different, so they are not related by rigid motion or even isometry. They have the same pair distribution function, so it's probably the simplest family of homometric sets, simply in the straight line. But they are easily distinguishable by PDD already by distances to the first neighbor. So you could see the differences here. Right? So when R is positive, PDD distinguishes them, but not PDF. Okay. Now going back from periodic case to finite, sorry about this back and forth, but very recently, so it was only 2 months ago, when we realized, well, we managed to formally write it down, but PDD is a complete isometry invariant, so on the isometry for any 4 points. So initially we did it in the plane, and yeah, more recently in July checked that it works in 3 dimensions and hence in any other dimension. For 4 points, it's complete. And this is indeed now an extension of the SSS theorem from 3 points to 4 points. So as a result, I show you what this PDD invariant reveals. We have seen these names, squares, rectangles, rhombi, parallelograms, so in this yellow area. These are familiar names from school. But we realized that space, well, obviously it's larger, it's 5-dimensional, 4 points in the plane. But it contains more interesting subspaces, families of quadrilaterals. So some of them are simple. So here you see actually any 3 points and the circumcenter. So center of the circle circumscribed around passing through all these 3 points. And in that case, the PDD matrix will contain a row with 3 equal identical distances. Also, you could have a chain of 3 equal distances. So these are like simple examples, but also we have found simply writing down the proof. So it emerged very naturally. But there is a family depending only on 2 parameters. I call them trisosceles quadrilaterals. Why trisosceles? Because here you see 3 pairs of equal distances. In total, we have 4 points, 6 distances. But if we have 3 equal pairs, it's a family of new quadrilaterals and actually related to rectangles. In what sense? Because in rectangles, we similarly have 3 pairs of equal distances, but in rectangles, all these distances have no common vertices, where like opposite edges and similarly diagonals. But if you remove that restriction, if you allow these edges to have common vertices, so isosceles triangles here, we get a new family depending only on 2 parameters. Right, so that was the case solved for 4 points. Actually, for 5 points, the problem is open. So you're welcome to contribute. Well, that's our conjecture that PDD is actually complete for any number of points in the plane. But in the three-dimensional space, there were known counterexamples already, constructed by Sergei Poznikov, for example, so equal PDDs. However, these counterexamples were very important for our research because we have understood what we need to do to strengthen the invariant and make it even stronger. So PDD was extended in 2 ways. If you use only distances, we constructed simplex-wise distance distribution. The idea is similar. So instead of fixing 1 point, we now fix a pair of points and write down pairs of distances to make the invariant stronger. And similarly, instead of pairs, we could take triples and so on, simplex-wise. In Euclidean space, we have more structure. For example, we could take the center of mass, so the geometric center of points, fix it at the origin, and then the only remaining ambiguity is under rotations. So this extra information, so fixing the center of mass at the origin, allows us to simplify this invariant. So we call it center distribution, but also we needed an extra step to guarantee Lipschitz continuity. This was actually the hardest bit because we wanted to distinguish mirror images not related by rigid motion in a continuous way. So that was the hardest bit. These are the references. But let me move to now comparison. So PDD matrix, even for the same number of original points, say 4 points, could have different sizes, as you have seen in examples. So let me see how we can let me explain how we can compare them continuously. So here on the left-hand side, you see the unit square lattice, very simple. So PDD is straightforward. Say up to 4 neighbors, it has distances equal to 1. So 1 row. But now, under very small perturbation, if I push that point up by 0.1 and this point down by 0.1, and also all the periodic translations, and keep these 2 points at exactly the same positions, then the unit cell quadruples. So motif is different. Now we have 4 points, and PDD matrix will, again, due to symmetry, will have 2 rows in this example. And since I have chosen very simple perturbations, you can easily check that these are the new numbers, new distances. And you see they changed only a little bit. Indeed, when we perturb 2 points up to epsilon in Euclidean distance, then the distance between them, interpoint distance, changes up to 2 epsilon only, right? So this is exactly what we see in for example, that first, that shortest distance between these perturbed points. So we extended that simple fact to PDD, and by using so-called earth movers distance, which basically minimizes the cost of matching weighted rows in 2 PDD matrices, or more generally in any weighted distributions. So in this particular case, it's easy to find with matching. So if you have only 1 row, of course, we should split it into 2 rows of weight 50% and compare them one by one. So the first half, the first row, the second half, the second row, and then take the weighted average. So the weighted average here is less than that this upper bound is expected. So a simple illustration. Now, when we started to compute our invariants on large data sets, so first it was Cambridge Structural Database. So already, actually, the average minimum distances, they distinguished all non-periodic crystals, but we used also PDD, so strong invariant, to make the following conclusion. So when we take only atomic centers, so forgetting about chemical elements, but atomic centers with precise enough coordinates given in the Cambridge Structural Database, we managed to distinguish all different, so non-isometric sets. More exactly, we have found a few examples where our invariants were the same, so distance 0. But when we looked at these examples, we realized that coordinates x, y, z, so fractional coordinates in C files were identical. So that's why, of course, our invariants were identical as well. So this was the first case of duplicates found. So many thanks to Dan, who implemented this algorithm and found the initial duplicates. So why do I include Richard Feynman here? Because even before we finished this experiment, I was reading his first lecture on physics called Chapter 1, Atoms in Motion. And that table and this picture are in his lecture. And when I saw this table, that was the Eureka moment for me, because I'm not sure what Feynman actually meant, what was he was thinking about, or other people reading this table. But for a mathematician, when I looked at this table, I unconsciously probably compared numbers, and I realized that all these numbers are different. What does it mean? It means that in this situation, the smallest interatomic distance, d, so it uniquely determines the cubic crystal, of course, this d is enough to distinguish all these chemically different crystals. Of course, it was only a simple example, but I realized that we should do the same by using our strong invariants on all crystals we can find. And that's what we did on the CSD initially, and more recently on other databases. ICSD materials project, you will see examples in Dan's talk and in Tatiana's talk as well. The more important conclusion, since we can distinguish all real periodic crystals by using pure geometry only, we can actually study them in a single space of isometric classes of periodic sets of points only, without taking into account any symmetry or any chemical composition. So this space is continuous. Of course, it's high dimensional. So for example, if you fix the number of points in a unit cell, it is fine dimensional, but still high. And all known crystals can be seen as visible stars in that space. So Dan will show the stars. But the universe is continuous. When I presented, so initially the first words Crystal Isometry Principle appeared in MACSMIN in 2021, but it was like an internal meeting. And my first external presentation was in March 22 in Southampton. And James Camby from Edinburgh, so proper chemist, when he saw that, he actually proposed a potential counterexample. And I have, let me illustrate this counterexample by using Mendeleev's table, because it involves potassium bromide and rubidium chloride. So potassium and rubidium, these are two neighbors in the periodic table here, and chloride and bromide also neighbors, but far away. So what he suggested, well, if you consider potassium bromide and then switch two elements to rubidium chloride, what might potentially in theory happen is that the distance, interatomic distance, remains the same in a cubic crystal. Possible in theory, and indeed I went to ICSD, so found examples. Actually, there are several, so you have a full list. And in one case, so for this pair, it was written exactly the same interatomic distance, 3.3, but with references to papers published in 1922. So it was exactly 100 years ago before when I looked. And I asked our colleagues here, so that's why Materials Innovation Factory is a great facility. So chemists can synthesize and check. So these are not complicated crystals. Mark Little, who is actually now in Edinburgh as well, so he synthesized these crystals and found the difference. So with modern instruments, they differ by 0.03 angstrom, so 2 decimal places are enough to distinguish. So not a counterexample, yes, Phil?
You find this one when you were doing a scan of the entire CSD as well?
No, so CSD, so Cambridge Structural Database, contains mostly organic crystals. They are more diverse. So this very symmetric.
As a counterpoint, heat one and cool the other, and then they're the same.
Second,
Heat the chloride, cool the bromide.
I agree. That's why I always say under the same ambient conditions. I completely agree. If you change temperature or pressure, you could, of course, artificially change these distances.
Fair enough. Okay.
Right? Yeah, no doubt you can do it.
What's the standard deviation on these experimental results?
Usually it's 3 up to 3 digits.
Below 1 angstrom, like 1,000th of an angstrom.
Yeah.
I mean, you have the ESU is somewhere in the 3rd digits usually.
So that's why 3 decimal places is our basic standard here. Of course, we understand that all our computations distances, they accumulate some floating point errors, but up to 3 decimal places we assume that we can distinguish distances. So this will appear also in fellow experiments. Okay, so as a result, what's our vision of a crystal universe? Crystal structure prediction, it outputs isolated collections of crystals, and previously we argued there was no continuous metric even between them. So the problem, what problem I stated earlier, is highly non-trivial. Ideally, to get a geographic style map, we would like to defog that space, and so instead of only approximations to local optima, we would like to see the full space, so beyond that fog, which is currently covering our crystal space. Right, now going back to point cloud invariants. You have seen some of these invariants in Yuri's talk this morning, although he focused on graphs, you remember, and I'm talking only about points without any edges. So recently we designed a new nested product distribution, so which is better for us because better than distances for the following reason. Even for 4 points, if you take 6 distances, even forgetting about triangle inequalities, they will not give you a point cloud because for 4 points in the plane, there is a tetrahedron of volume 0. And that means that these 6 distances should satisfy a non-trivial polynomial equation saying that the volume is 0. So you cannot choose them arbitrarily. But with projections, so scalar products, there is no problem. We have 100% realizability and even managed to prove not only Lipschitz continuity, but inverse continuity as well for these invariants. Yeah, no time to explain. There will be MIF++ seminar later where we'll go in more details. But briefly speaking, yeah, so similar picture to Yuri's talk. We fix a base point P, take the orthogonal vector and project all other points to this orthogonal basis. So the idea is simply in the plane, but actually we extended all these constructions to higher dimensions, which was much more complicated. So here is the comparison of QM9 molecules you have seen in Yuri's talk, but using only atoms, only points, no edges. So with this nested product distribution, we similarly get distance metric distinguishing all chemically different molecules. As a result, we argue, since this map from molecules to clouds of atomic centers is injective under rigid motion, yes, on that database so far, but also on the larger geom, we say that a molecular structure now can be rigorously defined as a class of atomic clouds under rigid motion. So in principle, in theory, we can reconstruct all chemical elements simply from precise enough geometry. And again, we show 3 decimal places in angstroms. So these examples of closest molecules. So chemically different, and we see a small difference between them, about 0.07 angstrom. And this example is even more interesting. Can you see the difference? So these molecules are very close. They're almost exact mirror images, but of course not exactly because of noise. So the difference here is these 2 hydrogen atoms. with two hydrogen atoms in front. That's why they are mirror images of each other with respect to that vertical plane. So our distance-based invariant gives distance almost 0 as expected, but we can easily distinguish them by our complete invariant with NBM, nested bottleneck metric. Again, back to the periodic case. PDD practically distinguished all crystals, but there were theoretical examples when PDD was the same. So this example is from Sergei Poznikov, and we designed invariants in this particular one periodic case to distinguish everything. So only one periodic case when it's a periodicity in one direction. So probably I'll skip this illustration why PDDs are the same, but the underlying periodic structures are different, and quickly go to isosets, which are our complete invariants. So recently with exactly computable metric. So the idea is to take local clusters around points, so with growing radius alpha around one. And now we record not only distances, but vectors. Yes, we remember that vectors, of course, are not invariant under rotations. We remember about that, but still, well, let's do it. If you have a different set, then these clusters might look differently, so different points. And these clusters allow us to partition all our points into different classes, so at a radius alpha. So on this set, we have only one class, so all points are like locally equivalent to each other at any alpha. But on this set, at a certain alpha, points are different. So they're differentiated into these alpha equivalence classes. So this differentiation stabilizes very quickly. When in practice, we have theoretical upper bounds when the stability occurs. And the talk by Teddy will discuss the bridge length and upper bounds for the stable radius. So let me skip that. And say that the resulting isoset invariant is the collection of classes of these alpha clusters at a stable radius. So what we formally proved that if we define it still a little bit abstractly as a set of classes under isometry with fixed centers, then the resulting isoset is a complete invariant. So unfortunately, one disadvantage that we defined a continuous metric, so Lipschitz continuous metric on these isosets, and even implemented, so Dan again implemented a polynomial time algorithm to approximate this metric. So we didn't have an exact algorithm yet, but we factor for approximation in the three-dimensional space. So this isoset with the recent metric almost solved the problem, almost, but we didn't have the exact metric. Is it really possible to implement an exact metric? What do you think? Oh, mission impossible. So that's our hierarchy. So I have almost finished. Average minimum distance, it's a vector. PDD, it's a matrix. We have a high order PDD version, which will be presented by Dan. Isoset was complete. So recently published with Lipschitz continuous metric, only an approximation algorithm. But even more recently, we designed a crystal rigid code combining isoset with our complete nested projection distribution on atomic clouds, so that we have an exact algorithm computing now and distinguishing everything. Yes, no, and the last slide, because I promised some new principle for you. So, of course, as you realized, we compared crystals globally, molecules globally, but now we look locally. So isosets are based on local alpha clusters. So let's look at chemical elements in QM9. So QM9, 2.4 million atoms across all molecules, only 5 elements. So it's really simple. All these 5 elements are here. But we also checked the conclusion on the much larger GEOM data set with 13 elements. Yes, still not the full periodic table. We remember it's larger, but we are moving. We are moving. And what we realized, that if we compute our distances with 3 digits in angstroms, then distances only to 4 or 5 neighbors are sufficient to distinguish all chemical elements. Distances to neighbors only. So this is the projection. So very simple. As usual, our first projection sorted radial distance to the first nearest neighbor, smallest distance, and the difference between distance to the second neighbor and first neighbor. And what do we see here? We see that all fluorine elements form an island completely separated from everything else. So it's, of course, it's a very simple projection to 2 dimensions, but we were surprised to see that fluorine now is completely characterized by only 2 very simple invariants. And even hydrogen is easily completely separated from everything else by using only 2 numbers. Yes, there is some mixture when different elements are projected to the same point, but actually this picture is produced with 2 decimal places in angstrom. So it's rough. With 3 decimal places, we have no confusion. You see, with 4 distances. So as a result, we claim it for a moment only for molecules. So if you have a real molecule, then precise enough geometry of an atomic neighborhood should determine any chemical element without any confusion. And so far we have demonstrated it on QM9 and GOM. Of course, we will test it on more experimental structures. So we think this principle will hold in more general situations with 1 important exception, but that's a story for the next MACSMIN in 2026. Thank you for today.